So today we're very happy to welcome Daniel Neuen, who will tell us about how to compress Fürer-Immermann graphs and what this means for the Weisfeiler-Leman algorithm. So Daniel, without further ado, please.
Thank you very much. Yeah, so I'm going to talk about compressing CFI graphs and lower bounds for Weisfeiler-Leman refinements. So this is joint work with Martin Grohe, Moritz Lichter, and Pascal Schweitzer. And yeah, we presented this paper at Fox last year. Okay, so let's get right into the topic. So that's not the right place. This is the right place. Okay, so yeah, I'm going to start with the graph isomorphism problem. So the problem is we are given two graphs, G1 and G2, and we want to decide whether they are isomorphic. So whether there is a bijection from the vertex set of the first graph to the vertex set of the second graph that preserves the edge relation. So edges are mapped to edges, and non-edges are mapped to non-edges. Okay, so this problem, well, it's easily seen to be in NP. We don't know whether it's in P. We have the famous quasi-polynomial time algorithm due to Babai from a few years ago. So yeah, this is a big open problem, whether this problem can be solved in polynomial time. And okay, so for this talk, we're not really going to look at the graph isomorphism problem, but we are interested in one particular heuristic for the graph isomorphism problem, which is this Weisfeiler-Leman algorithm from the title. Okay, so let me start by explaining this algorithm. And yeah, I'm going to start with the simplest version of the algorithm, which is the color refinement algorithm. Okay, so let's just look at an example to see how this works. So we are given one graph, and what we want to do is we want to classify vertices. So imagine now we don't want to compute isomorphisms between two graphs, but we are just given one graph and we want to compute the automorphism group. And in particular, we want to figure out whether different vertices of the graph can be mapped to each other by a symmetry of the graph. Okay, and well, what we are going to do is initially we are going to give every vertex the same color. So in the picture, every vertex gets the color red. To indicate that in the beginning we don't know anything. So at this moment, every vertex may be potentially mapped to every other vertex by a symmetry. Okay, and now the basic idea is to take vertex degrees into account. So what we can do is for each vertex, we can collect precisely the multi-set of colors that appear in the neighbors. So in the beginning, this is just the degree of the vertices. And we can take this information into account. So for example, you can see my mouse, right? Anyone?
Can you move it around a bit so that we can see?
Yeah.
It was visible before. I'm not sure now.
Okay, well.
I can see it.
Hope.
It's in the,
okay, so
in the middle
apparently
right.
It's visible. Yeah, in any ways, we can see we have different vertex degrees. So here there is a vertex of degree 4, and we have a vertex of some degree 7. So yeah, we know these cannot be mapped to each other by a symmetry. So now we can take this information into account and update our coloring. So that the new color is basically the combination of the old color red and the multi-set that we have that I put above the vertex. Okay, so we get this coloring now with 3 colors, and now we can repeat this process. So again, for every vertex, we collect the multi-set of colors that appear in the neighborhood. So for example, again, for this guy here on the top right, we have 2 blue neighbors, 1 red neighbor, and 1 green neighbor, and this is the multi-set that we put on top. And again, we can take this information into account. So for example, the 2 blue vertices here on the right, and you can see they have different multi-set. In the top multi-set, there is 1 red vertex. In the other multi-set, there are 2 red vertices. So again, we know that they cannot be mapped to each other by an automorphism, and we assign different colors.
Just to confirm that now I can see your mouse. So it wasn't visible before for some reason,
Perfect.
But now it disappeared again. Or now I can see it.
I think when I'm not moving it, it disappears. So
probably, yeah. Okay, great.
We'll see. Anyway, so we keep going with this process. So again, we collect the colors that appear in the neighborhood. And well, we can again look at this violet and this light blue vertex on the right. And we can again see that, oh no, sorry, we look at the 2 green vertices on the right. And we can see now, their multisets are different. So in one of them, we have a light blue neighbor. In the other, we have this violet neighbor. So again, we can assign different colors to them. And well, we keep going with this process until the coloring or the partition into color classes doesn't change anymore. Yeah, so here this happens after 3 iterations. You can see the 3 in the exponent of the CR on the left side. Yeah, so this, yeah, we have run color refinement for 3 iterations, and now we know that vertices with different colors cannot be mapped to each other. Okay, so this is the basic color refinement algorithm. Now, before I continue, let me present 2 alternative perspectives on this. So the first alternative perspective is a logical perspective on this algorithm. And now what we are trying to do is we are trying to distinguish vertices by writing formulas in first order logic, and we extend it by counting quantifiers of this form. Yeah, there exists at least n objects x so that phi holds. Okay, so let's maybe look at a concrete example. So for example, we can say, well, we want that our vertex x has exactly 4 neighbors. Yeah, so this there exists exactly 4. This is just some syntactic sugar. Yeah, with the notation above, you can realize that by saying there exists at least 4 neighbors and not there exists at least 5 neighbors. So yeah, this existential quantifier with an equal 4 in the exponent, you can realize with 2 existential quantifiers with greater or equal to 4 and greater or equal to 5. So yeah, this is just some syntactic sugar. And yeah, so we are saying we have exactly 4 neighbors. So this is before what we encoded via the blue color in this picture. Yeah, the blue vertices are exactly those with degree 4. And then we can say we have exactly 2 neighbors that were red before. Yeah, and red was encoded by having degree exactly 7. And we have another exactly 2 neighbors that have degree 4. And degree 4 is again encoded by the blue color. And what this means is basically we now encode blue vertices that have the multiset 2 red and 2 blue. Yeah, so this encodes basically, yeah, for example, this vertex here or this vertex or this vertex here will satisfy this formula. And this way you can see that, yeah, whenever you can distinguish 2 vertices with the color refinement algorithm, so assign different colors to their vertices, you can construct a corresponding formula. And what you can also see is that the quantifier depth of this formula, so the quantifier nesting. So here we have quantifier depth 2, because we have 2 nested quantifiers. This exactly corresponds to the number of iterations that we need to distinguish the 2 vertices. So for example, this vertex here, and let's say this vertex here with 2 red, 1 blue, and 1 green neighbors, we distinguish after 2 iterations. And this bottom guy is satisfied by the formula that I've written here, and this guy here is not, because it has this 1 green neighbor of degree 3. Okay, so now the formula that I've written here, it has 3 variables, x, y, and z. But if we are a little bit more economic with our use of variables, we can actually observe that we can do the same thing with 2 variables. Because in this scope here where we quantify the z variable, in this innermost quantification, we actually don't need this x anymore. So we can actually kind of rename this z to an x and kind of re-quantify this variable z. So with this, we now get kind of 2 variables, and we have kind of, quantifier depth corresponds to the number of iterations. And well, as you may imagine, this actually holds in general. So I will show a theorem in the slide after the next one. So this provides us some kind of logical perspective of the algorithm. And well, besides the logical perspective, there is also a game perspective on the algorithm. And this game perspective is going to be very important later on. So let me also explain this. Okay, so now we are given 2 graphs. So now I've copied the graph that we have been given. And well, we play a game on these 2 graphs. The 2 players are spoiler and duplicator. And well, it's a pebble game. So spoiler will always play pebbles on the graphs. And well, the role of duplicator is to play a bijection between the vertex sets of these 2 graphs. Okay, so let's suppose we are in this situation. So we have 2 pebbles. Now, 1 pebble, the orange pebble pair, is currently placed next to the graph, and well, we have the violet pebble pair. This is placed, so 1 violet pebble in the top graph is placed on a vertex, and we have another violet pebble placed on the vertex in the bottom graph. And well, you can see I've placed the 2 pebbles on vertices that will get different colors in the color refinement algorithm, because the multisets of the neighbors are different. And I now claim that spoiler can win this game. Okay, and again, yeah, I will try to explain it so that you can see the correspondence to the color refinement algorithm. So what will happen now is duplicator. Okay, so first of all, spoiler now decides that he wants to play the orange pebble, which is currently placed next to the graph. And duplicator now will have to play a bijection. And well, basically there are two options. So both of these vertices that are currently paralleled by violet, they have 4 neighbors. So either these 4 neighbors are not mapped to each other by the bijection. Well, in that case, we will see that we will win very quickly. So let's assume that they are mapped to each other. Well, then we can observe in the bottom graph, we have 1 green neighbor. And well, in the top graph, this green neighbor doesn't exist. Yeah, and this is now what spoiler will choose. So spoiler will choose the green vertex in the bottom graph. And we know in the top graph, we will play to a vertex that is not green, which in particular means that they have different degrees. Okay, so now spoiler can pick up the violet pebble and again ask for a bijection. And well, in the bottom graph, we have only 3 neighbors for the orange pebbled vertex. In the top graph, we have 4. So we know that one of the neighbors in the top graph must be mapped to a non-neighbor in the bottom graph. Yeah, and let's say this is this guy here that I have pebbled now in violet. And now in this situation, spoiler wins because in the top graph, the 2 pebbled vertices are connected by an edge, whereas in the bottom graph, they are not. Yeah, this is the winning condition for spoiler, that he wants to distinguish the graphs. And yeah, again, as is pretty much apparent from the example, when color refinement distinguishes 2 vertices, then we can transform this into a winning strategy for spoiler, just by following this outline that I've described. And again, this also holds in the other direction. Okay, so now this is the theorem that is kind of described here. So whenever we have 2 graphs and 2 vertices, so V is in a vertex of G and W is a vertex of H, then the following are equivalent. So color refinement after R iterations assigns different colors to V and W. This is the first bullet point. Or there is a formula which has 2 variables. So this is the 2 here in the subscript, and quantifier depth at most R. That's the R in the superscript, such that in G the formula is satisfied, whereas in H it's not. Or spoiler wins this bijective pebble game with starting position VW using at most R rounds and 2 pebbles. Okay, so that's the color refinement algorithm. Now, looking at what we can describe with this algorithm, well, it's not so difficult to see that we can't do a whole lot, because, for example, if you imagine that G and H are just D-regular graphs for the same D, well, then we cannot distinguish anything. Yeah, this you can see from running the color refinement algorithm. Yeah, we will always stick with this coloring where all vertices get the same color. Okay, so now we would like to kind of enhance the expressive power of this algorithm so that we can distinguish more graphs. And well, if you look at bullet points 2 and 3, that's kind of pretty obvious what we do. So in bullet point 2, we can increase the number of variables from 2 to any number k. And in the third bullet point, we can increase the number of pebbles from 2 to any number k that you would like. And well, the k-dimensional Weisfeiler-Leman is basically whatever then you have to put for the first bullet point so that you preserve this equivalence. Okay, so the definition of KVL is a little bit tedious, in particular if you haven't seen this before, so I don't want to explain this into too much detail. So if you want the formal definition, then just stick with, bullet point 2 or 3, whatever you find more convenient, the logical definition or the game definition. Still let me give maybe a very brief outline of how it works. So basically the idea now is, instead of coloring single vertices, as we did for the color refinement algorithm, we now color k-tuples of vertices. And maybe let's just look at a concrete example how this works for k equal to 2. Okay, so here's our graph. It's an 8 cycle. And well, with color refinement, initially we just gave all vertices the same color. So now we want to color 2 tuples. And here we can observe that there are 3 different types of 2 tuples. There are the 2 tuples which are diagonal of the form v, v. Then there are the 2 tuples vw that correspond to an edge. And we have the 2 tuples vw that correspond to a non-edge in the graph. And this is what we do for our initial coloring. So it goes like this. We have the three colors: violet for the diagonal entries, blue for the edges, and red for the non-edges. Okay, and now we can do the refinement. So remember, for color refinement, yeah, for each vertex, we build this multi-set. And here we were going to do the same. So now the only thing is that for each pair, we have to build a multi-set. Okay, and now, well, if I would draw a multi-set for each of these pairs, that would completely clutter up the picture. So let's just look at one of those pairs. So here is my pair VW. And, well, in the bottom, you can see the multi-set that I built. And, well, the basic idea is, well, on the bottom row, you have always these two vertices VW. And what you do for the top vertex in this multi-set is basically you iterate through all possible vertices of the graph, and then you collect the two colors that you have on the corresponding pairs. Yeah, so for example, this first guy here, this corresponds to this vertex here, where we have kind of from V to here we have blue, and from here to W we have blue. Yeah, the second one, this here, then the top vertex corresponds to the vertex V. Yeah, from V we get with this self loop to this guy, and then we take a red edge to get to W. And now you can do this for all of the vertices, and you get the multi-set. And this is the information that now you kind of put on this pair VW. And now you do the same. Yeah, pairs get different colors whenever the multi-sets are different. And when you do this, well, you get this coloring, because you can observe that these green edges, they have a blue-blue extension, whereas the red edges, or the red non-edges, depending on how you want to see it, they have no blue-blue extension. Okay, and now you can continue. We can again update the multi-sets, and we can again take this information into account. And now we will see that kind of, yeah, we have this diagonals that will be colored differently. Because now the red ones, they have a blue-green extension, whereas the yellow ones, they don't have a blue-green extension. They have only a green-green extension or a blue-red extension. Okay. Well, and in this case, for the 8th cycle, this is the stable coloring that you get. Okay. So that's all I want to say on the Weisfeiler-Leman algorithm.
Is it possible to say anything about looking at this beautiful picture? Like, what does this, is it possible to say, like, what does this tell us about the 8th cycle? I mean, and about, I don't know, automorphisms or whatever. I mean, is there anything I can read off from this picture? Or
well,
I should just not.
You can look at the automorphism group and look how it operates on the pairs. And I mean, pairs with different colors cannot be mapped to each other. Yeah, for example, I mean, with an automorphism, you cannot map a diagonal to a non-diagonal, which means you cannot map a yellow edge to a red edge, let's say. Yeah,
okay.
Does that answer the question, or?
I think so. So just to check that I got what you're saying, like suppose for an automorphism, I can look what it does to edges, and now sort of, since we're looking at pairs, sort of all edges have, or all vertex pairs really have colors, and however I map my automorphism, it has to preserve the color of edges, is what you said.
Exactly.
So
exactly.
Yeah, okay, makes sense. Thank you.
Sure. Okay, so this is what I want to say about the definition of the Weisfeiler-Leman algorithm. So now let me tell you a little bit about why this is interesting. So, So first of all, I have to mention that the equivalence that we have seen for color refinement still holds. Yeah, so we have this equivalence between Weisfeiler-Leman, also R rounds of Weisfeiler-Leman, yeah, and formulas with k+1 variables and quantifier depth R, and the bijective pebble game with k+1 pebbles and R rounds. Yeah, note that the round numbers, they are always the same. So here we have always an R, but kind of here we have k versus k+1 variables and k+1 pebbles. Yeah, so the color refinement algorithm that we have seen in the beginning corresponds to 1 WL. Okay, so this is just something to keep in mind, that there is this off by 1 with the dimension or the pebble number or variable number. Okay, so with this, now why this is interesting. So yeah, I've already mentioned the application to the graph isomorphism problem, but as it turns out, the Weisfeiler-Leman algorithm has also a lot of surprising connections to other areas. So we have seen the connection to logic, yeah, to this k+1 variable fragment of first-order logic with counting, and also the connection to games that I've just mentioned. But yeah, beyond that, in recent years, also various other connections have been discovered. So for example, there is also a characterization of Weisfeiler-Leman in terms of homomorphism counts. Yeah, or we can also kind of characterize Weisfeiler-Leman by writing linear programs for graph isomorphism and looking at some extensions like Scherali-Adams hierarchy or Lasserre hierarchy, or you can also do corresponding things with proof complexity. And yeah, also a very big thing in recent years is this connection to machine learning, in particular because the Weisfeiler-Leman algorithm can be used to describe the expressive power of graph neural networks. Machine learning people have also been very much interested in the expressive power of the Weisfeiler-Leman algorithm due to this connection. Okay, so there is a lot of motivation to study this algorithm. And well, essentially, there are kind of two parameters of this algorithm that you can study. The one parameter is the dimension, the k, the length of the tuple that you colors. And yeah, if you run KWL, what kind of things can you express or what kind of things can you find out about the graph? This is not what we are going to do in this work. But in this work, we are interested in the second parameter, which is the iteration number of the Weisfeiler-Leman algorithm. So for how many rounds do I have to run this algorithm until it stabilizes? Okay, so this is the main question that we want to study here. So what is the iteration number of KWL, which means what's the number of refinement round it takes to reach a stable coloring? Yeah, and again, if you remember this equivalence theorem, this is, for example, well motivated by this game and this logic perspective, because in the logic perspective, this exactly corresponds to quantifier rank, whereas in the game perspective, it corresponds exactly to the number of rounds that you need. And also, if you look at these other areas, there are also somehow connections that give iteration number. Yeah, there is always some corresponding meaning that also motivates it from other perspectives. Okay, so what is known about the iteration number? Well, we can start off by observing a trivial upper bound. Yeah, so think of the color refinement algorithm where we color vertices, and you can look at the partition into color classes. Yeah, in each round, the number of classes in this partition has to increase by at least one. So this means if you make so you can make at most n-1 refinement steps. Yeah, and similarly, if you color k-tuples, then you can make at most n to the k-1 refinement steps. Okay, so this is the trivial upper bound that we get. So for k equals to 1, it actually turns out that this trivial upper bound is tight. So we can actually find graphs where you really need this n-1 iterations to reach the stable coloring. So this was proved by Sandra Kiefer and Brendan McKay, ICALP 2020. And yeah, it's a really nice and elegant construction that achieves this matching lower bound. Okay, so for k equal to 1, the situation is entirely clear. So let's look at the higher k. And well, here it turns out that we can actually get improved upper bounds. So the first work in this direction was by Sandra Kiefer and Pascal Schweitzer, LIX 2016. And they proved that for k equal to 2, you can shave off a log n factor, basically from the trivial upper bound. And well, as it usually is, after this, first step where we shave off a little bit, then people started to look at it. And a few years later, Lichter et al., so Moritz Lichter, Ponomarenko and Pascal Schweitzer, they managed to improve this to almost linear. So order n log n iterations are needed. And for k equal to 2, this is almost tight because Martin Fürer in 2001 actually proved a lower bound that you need at least omega of n rounds on KWL. Okay, so for k equal to 2, we're almost there. There is only this log factor that is missing. Okay, so what's the situation for bigger k? Well, in 2016...
So for these lower bounds? Sorry, I mean, this is like just to be because these are like families of graphs that exhibit, or wait,
Yes.
and I can't, are there any, these are graphs we know, or are they just glued together like completely new things, or is there anything interesting that can be said about these graphs?
You mean the Fürer graphs? Well, I will describe this on the next slide. So maybe we can postpone this.
Okay, okay, thanks.
Yeah, so let me continue with what's known. Okay, so then yeah, Christoph Bergholz and Jakob Nordström in 2016 leaks, they improved the lower bound to n to the omega k over log k, albeit with the caveat that they didn't manage to construct graphs, but relational structures. And these relational structures actually have arity k. And moreover, if you look at the size of these relational structures, they're actually quite big. So they have size roughly n to the order k. So if you look at this lower bound from a size perspective, then this doesn't even achieve a linear lower bound. But of course, it's very nice in terms of the number of vertices because, well, it gets fairly close to the upper bound. And well, then, well, a subset of the authors stood together with Martin Grohe and Moritz Lichter, LIX 2023. Well, we managed to improve this lower bound a little bit, so we managed to shave off the log k factor, but we still have this caveat of relational structures that are k-ary and still quite big. And in the same work, we also managed to kind of improve the upper bound a bit. So basically, we generalized this n log n from Lichter et al. From 2019, to say that we can shave off this one n factor, also for bigger k. So we get n to the k minus 1 log n. Okay, so this is the kind of the situation before this work. And the main result of this work is an improved lower bound of omega of n to the k over 2. And well, this has two advantages. So the first advantage is that we get kind of this omega k here in the exponent. We have proved to a concrete kind of k over 2. Yeah, so we can really give a concrete dependence on this. So k over 2. But in my opinion, the even bigger advantage is that what we construct here are actually graphs and not relational structures, which in particular means graphs can have at most n square edges, so size at most n square. So in particular, this is also a superlinear lower bound in the size of the structures that we construct. Okay, and this is basically what I want to describe now, how we can get this lower bound. Okay, and well, as I already indicated, the starting point of our construction is this lower bound from Fürer from 2001, which provides this linear lower bound. So what I want to do now first is I want to briefly recap how this omega of n lower bound works, and then we will see how we can improve this. Okay, and for this, so here is again the main result stated. So the maximum iteration number of KVL on graphs is omega of n to the k over 2. Okay, so now onto this linear lower bound from Fürer. And for this, we have to look at the Fürer-Immermann construction. Okay, so in this kind of first part of the talk, I don't want to formally define this construction and describe all the properties, but I just want to give you a main idea. Okay, so basically what happens is we take a base graph. So in this case, the base graph is a 2x5 grid. Yeah, so basically each vertex of this 2x5 grid corresponds to one of these big colored bubbles here. And then what we do is we replace basically each of these, or in each of these bubbles, we put a certain gadget. And well, the main thing that you can look at here is now how these gadgets are connected. Yeah, basically for each edge of this 2x5 grid, we here have this parallel connection. Yeah, so we have kind of these two vertices here in the light blue bubble and these two vertices here in the pink bubble, and they're connected by two parallel edges. And now what you can alternatively do is you can kind of, instead of connecting them in parallel, you can basically kind of connect them, kind of with a cross. And well, this will give you a different graph. And the key property now is that it doesn't matter where you put this cross. So basically, whether you put this cross here between green and blue, or whether you put this cross here between blue and orange, or between orange and black, basically this is always the same graph. Yeah, all of these graphs where you put this cross somewhere, they're all isomorphic. And kind of on top of that, you can also put some larger number of crosses, and the isomorphism type only depends on the parity of the number of crosses. Yeah, so basically you can have the top graph where you have 0 crosses or any even number of crosses that are placed wherever you want. And you have the bottom graph where you have an odd number of crosses placed wherever you want. And in this case, we have this one cross between orange and black. Okay, and these two graphs are non-isomorphic, but yeah, they are somehow different to distinguish because, yeah, essentially this cross, this can be anywhere in the bottom graph. And yeah, we cannot really pinpoint this location because all of these graphs are the same. Okay, so now the question is, well, can Weisfeiler-Leman distinguish these two graphs, and how long does it take? And well, what we can do now is we can kind of look at this from the perspective of the pebble game. So let's imagine in the pebble game we place a red pebble into this blue gadget. And generally, we will always try to place these pebbles into the middle part of these gadgets, and so these 4 vertices that are located in the middle. So in a way, what this means is that now we cannot move this cross through this blue gadget. Yeah, so basically what happens if you move the cross from here to here, you will have to apply a permutation to these blue vertices. Yeah, so apply an automorphism to this blue gadget that allows you to move the twist from one end to the other. And the main point is once I place a pebble on this blue thing, then kind of this automorphism is no longer allowed because it's kind of fixed now. And this means I cannot move this cross through the blue thing.
And this is because of subtle properties of this blue gadget that you're not going into details about. But somehow once you have 2 guys inside the blue gadget, you cannot.
Yes,
okay.
You basically then the blue gadget is completely fixed and you cannot move around anything. So there are no automorphisms left in a way. And you need these automorphisms to kind of move this twist from one end to the other.
Yes. Mm-hmm.
Okay, so this allows us now to take an abstract perspective on this game. Yeah, so basically where we have this 2x5 grid and this cross is located somewhere. So I've drawn this here. Yeah, the cross is located here on this edge. And whenever we place a pebble, we say that the corresponding vertex or the corresponding gadget is locked because now we cannot move this this cross through there. Yeah, now what we want to do is we want to capture the cross. And well, this should hopefully remind you of a very familiar type of game in graph theory, which is a cops and robber game. Yeah, which basically these locks correspond to the cops and the cross corresponds to the robber. And now we want to place these locks to eventually capture the robber or the cross. And this is what we can do here. So basically now the next we lock this vertex here with the blue lock and a corresponding pebble. Then maybe we kind of move the twist to the end, which means we have to specify a path along which we can move this cross, which only goes through non-locked vertices. So now the twist is located here, and then we keep playing. Maybe next we lock this vertex, and then maybe we move the lock from here to here, which corresponds to moving a pebble, and eventually we move the green pebble into the green gadget and lock the corresponding vertex, and now we have kind of fixed the twist. Okay, so just to be a little bit precise, so if you look at the graph on the top, you will see that we have not yet won because, well, in both graphs, we will have a non-edge between green and red pebble. But now basically you can go one step kind of to the middle and pebble these 2 vertices next. And then you will be at the point where in one graph you have an edge and in the other graph you have a non-edge. So basically up to 2 rounds, so an additive factor of 2 rounds, the round numbers and kind of pebble and cop numbers, they all correspond to each other. Okay, so this means we can take this abstract perspective. And well, this essentially now gives the linear lower bound because if I have k plus 1 cops, then I can look at the k by n grid. Yeah, and I can start in the middle, like we have done here essentially, and kind of the cross is located at one of the 2 ends, and I have to move the slowly the separator from the middle to one of the two ends to catch the twist. And this takes omega of n rounds. Okay. So these are the results that we get. So if we have a k by n grid, it takes omega of n rounds to capture the twists using k+1 logs in these games. And this exactly corresponds to the cops and robber game, maybe with the only difference that the robber is placed on an edge here in our game, whereas usually it's placed on a vertex, but you can easily check that this does not make any difference. And, well, via the CFI construction, this means that spoiler requires omega of n rounds to distinguish the two corresponding CFI graphs. Okay, so this gives the linear lower bound of Fürer. And this is now what we want to improve. And, well, the very basic idea is that we want to repeat this construction, but we want to use less vertices in the CFI construction. Yeah, so if I can basically get all the properties here, but use less vertices, then if I measure in terms of the number of vertices, this will increase the round number. So this is kind of the idea. Okay, so how are we going to save vertices? Well, the idea is kind of very simple. So if we remember this CFI construction, basically for each of these bubbles or for each of these gadgets, we used new vertices. And what we are now going to do is, for some of these gadgets, we will kind of reuse vertices multiple times. Okay, so the idea that you should have in mind is, here is again the picture that we had before. And now we will kind of place an equivalence relation on the vertices of our base graph. So here we have now kind of this orange relation, which says, well, these two vertices, they will be equivalent. And what this means in the CFI graph, well, we can kind of naturally identify the vertices in the gadget. And you can kind of imagine shifting the blue bubble onto the orange bubble. And this gives you an identification of the vertices, like this. And then I will just identify the corresponding vertices. Yeah, so each orange edge in the bottom picture, I just contract. Okay, and this way I reduce the number of vertices. Okay, so this sounds like an interesting idea. So let's explore this. And the key question to ask here now is, what does this do to our to the cops and robber game? Or in other ways, or formulated in a slightly different way. So basically before, we described this cops and robber game as a correspondence to our Pebble game. And now the question is, how do we have to adopt this cops and robber game so that still we preserve this correspondence, but after contracting all of these orange edges in the bottom part? Okay, so there are kind of two very natural things that you have to do here. So the first one kind of corresponds the moves of the cops. Yeah, so if you move a cop to, let's say, this vertex here, well, then it's kind of natural that we also place a cop on the other vertex. Because in the CFI construction, after we contract these orange edges, kind of these two gadgets here are the same, the green and the orange one. So kind of both will be locked at the same time if we pebble a vertex there, which kind of corresponds that we, in the base graph with this equivalence relation, we also lock both vertices at the same time. Yeah, so cops are now placed on equivalence classes of vertices instead of single vertices. Okay, so that's kind of the more obvious issue. There's also a more subtle issue here, and this corresponds or this concerns the moves of the robber or the twist. And these paths also have to be compatible. And compatible here means is, let's look at this vertex here. So this vertex here, if I look at this pink path, I enter from the left and I leave to the bottom. And basically I will have to do the same for all equivalent vertices. Yeah, so this path here is not compatible because this vertex here is not touched at all. But I can kind of modify my path to look like this, and then it's okay again. Yeah, because now here I enter from the left and leave to the bottom, and here I do the same. And this kind of corresponds to automorphisms. Yeah, if I kind of have this pattern here, on this vertex, then when I want to move the twist, this corresponds to some automorphism of this gadget. I have to permute the vertices in some way. And because vertices here are identical, I will have to apply the same permutation here. And this means I have to do kind of the same movement of the twist through this gadget. Okay, so now this gives us a modified game. Yeah, cops are placed on equivalence classes, and the robber has to respect, the paths of the robber have to respect these things, have to be compatible. And now we can wonder, how many rounds does it take? And basically what we want to do is now we want to build equivalence classes as large as possible while essentially preserving the round number. And to be more precise, we don't only want to preserve the round number, but we essentially want to preserve this escape strategy of the robber that we had before. Yeah, remember before, the escape strategy is essentially, so whenever the cops do not play a separator in our grid, then we can kind of move between the two ends of the grid. And well, whenever a separator is placed, then we always move to the end that is further away from our separator. Yeah, and then the cops slowly have to move the separator to the corresponding end. And this now we want to simulate with equivalence relations so that its equivalence classes are as large as possible so that we can save as many vertices as possible in our construction. Okay. So here is the main idea for the equivalence relations or the compression. So let's consider a 4x(n) grid. And what we are going to do is for each row, we are going to set a period. I will call this pi. And we will say that two vertices are equivalent, well, whenever their distance is basically divisible by this period. Okay, so here is a picture. So for example, let's say in the first row, I choose period 3. And then I will have the corresponding equivalence relation. So whenever vertices are away a multiple of 3, then I will declare them to be equivalent. And this is not only for the class that I have drawn here, but also for these guys here. And for the bottom two rows, I, let's say, choose period 5. Okay. And well, when you do this, now we can have one very nice observation. Namely, since we have chosen two prime numbers, 3 and 5, and we can look at their least common multiple, this is 15, their product. And now if we place kind of one log in each row, then what will happen is, because this grid has length at most 15, it will happen that we will have only one column can be completely blocked by these logs. And this is now the main property that we're going to use, because what this means essentially is if we place one log in each row, then we can still kind of exactly locate one separator. Yeah, similarly to before. Okay, so there is one subtle issue here. In order for there to be a separator, okay, let me formulate it differently. Well, one way to have a separator is basically to block one column, but that's not the only option. So for example, here we also have a separator, although we do not have blocked one column. But this we can easily fix by kind of increasing the periods a little bit. So concretely, what we will do is in this, or what we can do in this k equal to 4 case, we can choose two large primes, q and q prime, and set our periods to be equal to 2k plus 1 times q and 2k plus 1 times q prime. And this factor 2k plus 1 essentially means that, I make the grid a little bit longer in the end, so that now this guy here is no longer a separator because there are kind of lots of columns in between there, precisely 2k plus 1 many. And this, now you get exactly this property that you have exactly, or at most one separator if you place a log in every row. And this is basically what allows us to, maintain the previous strategy. Okay, and now if you kind of do a count of things, you can basically observe that the length of the grid that we construct here, this is roughly w square. So this will be the number of rounds that we need, because round number is the length of the grid, but size after the compression of the CFI graphs is only theta of w, because in each row we basically after this compression, or let's say we have only roughly W many equivalence relations, or equivalence classes, sorry. Now, because in this row here, we have kind of Q prime many equivalence classes, because after every Q prime steps, we get, we have this period that takes effect, or roughly times 2k plus 1. Okay, so with this, you can see we will get basically this quadratic blow up here. Now we have O of W or theta of W many vertices, but we need theta of W square many rounds. Okay, and now let me, quickly mention why this works. So kind of the main thing is, if the lockers or the cops now try to kind of move towards our twist at one end of the grid too fast, then we can move it to the other end. And well, let's say, for example, now the locker decides to make this move here. Yeah, so that now essentially we haven't placed a separator. Yeah, then we can use, in this case, that we have the same period on the bottom two paths here, which allows us to actually build a periodic path that that satisfies this compatibility condition. Yeah, so the fact is that before, in the last two rows, I actually chose the same period. This was not a coincidence. It was actually by design, so that I have the possibility to build these periodic paths, because both of these rows have the same period. So this path is actually compatible. Okay. Yeah, and this basically allows us, whenever not a separator is placed, then we can move our twist from one end to the other. So really, omega of W squares rounds are needed to win. Okay. And well, this you can now easily generalize at least to all even k. Yeah, basically, you choose k over 2 many primes, and for each pair of rows, of successive rows, you assign one prime number. And then you have always these pairs that you can use to construct these periodic paths. Okay. For odd k, you can also do this by basically having one group of size 3 instead of size 2. And what this will give you is a lower bound of n to the omega k over 2 floor here. Yes. Okay, so this is the main idea for the construction. Since I think I'm running out of time, let me very briefly mention. So if you remember,
I mean, we started a bit late also, so I think you can.
Yeah, but I think
take your time.
I don't know.
Okay, whatever.
Yeah. I think there will be time to discuss things in more detail in the technical section. So let me leave it at this kind of brief overview here. And quickly mention, so here we get n to the k over 2 with the floor. In the main result, I had n to the k over 2 without the floor. So this you can also achieve with a slight modification of the construction. And now what we will do is we will basically, so here I have done the construction for k equal to 3, where we have a grid of height 3, where we basically choose 3 primes and we put 2 primes in every row. Yeah, so for example, for the first row, the period will now be q times q prime. For the second row, it will be q prime times q2 prime, and for the third row correspondingly. And well, the basic idea is kind of, if you want to move things along the period q prime, then you can kind of use rows 1 and 2 to build this periodic path again. Yeah, so basically for every prime, we have one pair of rows, which we can use to build this periodic path, where kind of the period appears in both rows, so that we have this compatibility condition when we want to move the twist from one end to the other. Yeah, this is very, very important. And then again, if you do the math, you will see that you get, in this case, n to the 1.5. Yeah, your grid will have length w to the 3, and the size of the CFI construction here will be w square. Okay. So this way you can construct a lower bound of n to the k over 2 without the floor. Okay. So this is what I want to say on the construction, at least for the moment. So, let me briefly conclude. So here is the overview of the upper and lower bounds again that we currently have. So the situation is completely settled for k equal to 1. Well, for k equal to 2, there still is this annoying log n factor between the upper and the lower bound. So this is one thing that would be nice to remove. And if we look at larger k, now we have this gap between n to the k minus 1 in the upper bound and n to the k over 2 in the lower bound. So this is one thing that would be nice to if we can close that. So this is the first question here. One other question that is also very interesting is this question about trade-offs here. So let me briefly explain what I mean by that. So trade-off here refers basically to trade-offs between increasing the number of variables and keeping or looking at the iteration number. So if you look at this grid example again, so let me go here. Let's suppose now, so here we have played the game with 4 cops. And now imagine that you increase the number of pebbles or the number of cops to, let's say, I don't know, 20 cops. Yeah, then in this example, you can play a lot quicker because basically with this larger number of cops, you can implement some kind of binary search strategy. Yeah, you can kind of block 3 vertices in the middle, and then the robber has to be on one of the 2 sides. Let's say it's on the left side. And then the left side you can again cut in half. Because you have some additional cops, you can place new cops on another separator. Yeah, and then you have already located or you kind of restricted the cop to 1/4 of the graph. And now you can basically keep going like that, implementing a binary search strategy, and this will terminate after log n rounds. And what this means in the construction that we have, also in our compressed construction, if we increase the number of cops or the number of pebbles or the dimension of the Weisfeiler-Leman algorithm by some fixed constant, then the round number actually drops dramatically to order log n. And the question here in this trade-off question is whether we can do some kind of different construction where the round number remains large even if the number of pebbles increases. And here I can just mention that with the constructions that we have before, so these relational structures constructions that achieved n to the omega of k lower bounds, they are actually robust in this sense. So they're increasing the number of variables or pebbles does not lead to a drop or not lead to a significant drop in the round number. Yeah, so the question here is, can we also achieve this for graphs? Okay, and then last but not least, we have seen Weisfeiler-Leman is connected to a lot of other areas. So can we kind of use this new construction also in these connected areas or some other areas? And we believe one possible, one very natural area would be proof complexity. And I think I will stop here for the moment, and thank you for your attention.
Thank you so much, Daniel. I'm sort of applauding on behalf of everybody. So, and there are some also applause emojis showing up in the participant list. So, any questions at this point from the audience? I guess one question that I guess you've thought about maybe, and I don't know if it's possible to say anything, but somehow we are very dependent here on that we have this long narrow grids.
Yes.
Is there any way of sort of abstracting away and saying I want to think about graphs more in general and sort of do something similar, whatever that might mean, or
well, I guess that's the question. Yes, how to do this? This is the thing that we haven't figured out. I mean, the compression and everything you can do in general, and I mean then it's just about on general graphs finding sort of different equivalence relations so that this cops and robber game with the equivalence classes is still somehow leads to good lower bounds. And this is exactly the question how to do this. And we may have some ideas which I probably don't want to say too much about, but
fair enough.
This is what you have to figure out.
Yeah. Because this is like, I mean, this construction is like pure magic somehow. I mean, it's just, it's amazing.
Yes,
but it's...
definitely. It's yeah, it's a really nice construction, and somehow yeah, I believe there is potential to do this somehow on other graphs, but it's not obvious at all how to do this. And I think in general what one has to do also to some extent is kind of, yeah, better understand how, or let's say maybe understand different ways of how this proof can be done. Because at the moment, the proof is very much based on sort of having automorphisms to move the twist from one end to the other. But with the standard CFI graphs, we have also kind of lots of other arguments to do these things. In particular, their kind of local arguments are available that kind of only look at a small portion of the graph and argue about things. And I think one big question is, what does this mean in compressed graphs? Can we somehow find an analog there, where we don't have to argue with automorphisms, but in some other way? And probably this will be one of the key steps if one really wants to go beyond these grids and long, narrow things. And yeah.
So the way these final graphs look like, just to understand, when you're doing all of these identifications, should I think of the edges incident to a vertex in the final graph is going to be like the union of like all edges for all vertices in this equivalence class, so that the vertex degree goes up by a factor W or something?
Yes.
Okay.
I mean, of course, also some of the edges will be identified.
Yeah.
But yes. Yeah. So if you look at one row, then basically inside of one row there, you will still have only few edges because of this periodicity. But if you look between the rows there, you will have really high degree.
And is it sort of clear that you couldn't? Okay, so maybe this is obvious, but let's suppose for some reason I'm interested in bounded degree graphs. Like, is it clear that, like, if I restrict my attention to bounded degree graphs, then I could never get this super linear kind of behavior in terms of iteration number?
Well, at least it seems, well, it's yeah.
Maybe it's obvious.
Not so clear. I mean, because I mean, whenever you identify things, you may also identify edges, and maybe you can find some clever way of building the equivalence relations so that you also identify so many edges that in the end you have still bounded degree. Although at least intuitively that sounds it sounds difficult to achieve, let's say.
Any other questions? I'm soon going to have a well-deserved break. I'm just looking if there's, I mean, there will also be ample opportunities to ask questions after the break. So I think we're thanking you again, Daniel, for an amazing talk. I mean, and the pictures are also like extremely helpful to especially this higher dimensional Weisfeiler-Leman. This picture was just amazing. I mean, it's really helpful. So thank you so much. So we're back after the break, and it's over to Daniel again for the technical second half.
Okay. Yeah, so I think this part will be somewhat more interactive. So I have prepared some slides, and behind me there is a big whiteboard that I can use, and hopefully you can see. Yeah, so let me start with the slides, and yeah, whenever there is something unclear or something should be explained in more detail, feel free to interrupt, and I can put things on the whiteboard. And apart from that, I will, at least at the beginning, follow the slides that I have. So let me share my screen with the technical slides. Okay. Great. So let's get into technical details. And yeah, I have chosen a few things that I want to explain in more detail. If you would like to see other things, you know, feel free to ask. And I have the whiteboard behind me, so I will do my best to explain them. Okay. So getting into details, I want to start with the bijective pebble game. Okay, so before I do that, let me maybe start with a brief overview of what I have planned. So there are roughly two parts. The first part will be on this connection between the bijective pebble game and this cops and robber game and the details of the CFI construction. And basically kind of all the way up to we're at this point where we know we have to construct graphs with these equivalence relations where sort of the cops require a large number of rounds in terms of the number of equivalence classes. And then the second part will be on the grid and actually describing these equivalence classes and how we can get the round lower bound for this specific game. Okay. So I will start with the first part, and in the first part, basically everything regarding Weisfeiler-Leman is done via this bijective pebble game. Yeah, so as you may remember from the last talk, this equivalence between Weisfeiler-Leman and this bijective pebble game is well known. So from now on, I will kind of ignore the Weisfeiler-Leman algorithm, put it aside, and we will just work with this bijective pebble game because this turns out to be the best perspective here.
Just to clarify for us non-experts in these pebble games, I mean, there's also this Ehrenfurst phrase thingy, but then you usually just place like pebbles one at a time. But the twist here is that somehow the duplicator has to play a whole bijection and let the spoiler choose.
Yes. So the bijection, intuitively speaking, corresponds to the ability to count. Yeah, you have these counting quantifiers and kind of the bijection set. If you have a different numbers of vertices that are, let's say, green, then you will be able to capture this via the bijection.
Okay, so the fragment with like standard quantifiers, it would be the standard Ehrenfurst phrase where you just play on either one of the structures, and since you can count, now you have these. You can force duplicator to make stronger or more restrictive moves, sort of. Okay.
Yes, precisely. Okay, so here is the informal description or the picture description that we have seen in the first part of the talk already. So let me just remind you, here we have the two pebble pairs, the orange pebble pair and the violet pebble pair. The violet pebble pair is now already placed on the graph. So I've placed it on these two blue vertices, but with different multisets. And again, now duplicator placed the bijection. At the moment, both vertices have degree 4. So let's suppose the bijection preserves the neighborhood. But then we can kind of move to this green vertex in the bottom part and have some corresponding vertex in the top part, which is now blue. So now they will have different degrees. The bottom one, the orange pebbled vertex, has degree 3. In the top part, it has degree 4. And now, well, kind of, spoiler takes away the violet pebble because he wants to play it again. Duplicator plays the bijection. And, well, one of the neighbors in the top graph must be mapped to a non-neighbor in the bottom graph. And then we win. Okay, so here is the bijective pebble game described a little bit more formally. So we have our two players, spoiler and duplicator. We play in rounds. We have k pebble pairs, which I will denote by pi and qi. They're initially all placed besides the graph, or well, if you maybe sometimes you want to also have a starting position. So in the example on the last slide, the first pebble pair was already placed. And well, each round consists of the following steps. Spoiler picks up a pebble pair, pi, qi. Then duplicator chooses the bijection. And then spoiler chooses a vertex in the first graph, vi. And well, we get the corresponding image according to the bijection in the second graph. And this is where we place our pi-th pebble pair on. So pi goes onto vi in G and qi goes onto wi in H. And spoiler wins the game in some round if they're ij, so that, well, we have either edge relation is not preserved, so vi, vj is an edge in G, and wi, wj is not an edge in H, or the other way around. Or the other option is that equalities between things are not preserved. So in the one graph, orange and violet are placed on the same graph, the two pebbles, and in the other graph, they are not placed on the same vertex. Then spoiler also wins. Okay. Oh, sorry. Okay, so this is basically this game we want to investigate. And with this, we can kind of reformulate the result. So if we have a fixed k greater or equal to 2, then for every n greater or equal to 1, we can construct graphs G and Hn, which have order of n vertices. Spoiler, can win the k+1 bijective pebble game. So here I formulated it again with k+1 because this is kind of, this corresponds to kWL. But yeah, in order to win, a lot of rounds are required, namely at least omega of n to the k over 2. Yeah, and then with this equivalence between WL and this game, we get as a corollary that the maximum iteration number of kWL on graphs is omega of n to the k over 2. Okay, so the details that I want to describe now are on the, we will prove the top theorem. Okay, so as you know from the first part, it will all be about Fürer-Immermann graphs. So now let me describe Fürer-Immermann graphs a little bit more formal. Okay, so what we are going to do is we will work with ordered base graphs. So an ordered graph is just a graph which has a linear order on its vertices. You may just think that vertices are numbered 1 through n, and then you get a natural linear order. And well, one important thing here is that if you have a linear order on the vertices, then it also induces a linear order on the neighbors of each vertex. Yeah, so if I look at some vertex v in my vertex set of G, then I say that the ith neighbor of v is the ith element in this order. Yeah, so if I have 4 neighbors, then I have a first neighbor, a second neighbor, a third neighbor, and a fourth neighbor. Yeah, according to the linear order that I have globally fixed on my vertex set. Okay. So with this, I can now define CFI graphs. Here I'm going to define them in a slightly different way than the picture I have shown you in the first part of the talk. So I will stick to the things that we do in the paper.
The curiosity.
Thing is, yeah.
Maybe it's not important at all, but is it important that you have this global linear order? I mean, you could also, I guess, think of every vertex just deciding about its first, second, third, fourth neighbor, or that would not be good?
That depends on how we describe things. So having this linear order is kind of convenient for describing the identification later on.
Okay.
So I can say a few words about this at a later point, maybe. And then it may become more clear. Okay, so in any case, let's for now assume that we have this linear order. And now we can describe the CFI graph over this ordered base graph G. And well, we also get the function that maps edges to elements of the 2-element field F2. Okay, so the CFI graph, CFI GF, is defined as follows. So we have vertices of the form v, a1 up to ad, whereas these ai are elements of the 2-element field, and they sum up to 0 over F2. And we do this for every vertex v and v of G, where there's degree is d is the degree of the vertex. Yeah, so if I have a vertex of degree 3, let's say, as in the picture, then I consider these 3 tuples. I have 4 vertices, all that adds up to 0. Yeah, so I have in the picture here, let's see, so here I have the 0, 0, 0 tuple, I have the 1, 1, 0 tuple, the 0, 1, 1 tuple, and the 1, 0, 1 tuple. Now these are all tuples over F2 that sum up to 0. Okay, and now I have to connect vertices. And when do I connect 2 such vertices, v bar a and w bar b? Well, first of all, v and w should be connected by an edge. And well, now I have to look at this, So let's suppose v is the ith neighbor of w. Yeah, so here in the picture, this is marked by red. So here w is the second neighbor of v, which is why I marked the second column here. And v is the third neighbor of w, which is I marked the third column here. Okay, and then I put an edge whenever aj plus bi is equal to the f of this edge. Okay, so what does this mean? Let's suppose the f of this edge VW is 0. Yeah, then I connect whenever the two corresponding entries add up to 0, which is also this the same as saying that they're equal over f2. Yeah, so you can see here I connect 0, red 0 here with red 0 here, and this red 0 also with the red 0 here. And here I connect the red 1 here whenever there is a red 1 here. And well, now if f of VW would have been 1, I would just flip this. Yeah, so then I would basically connect whenever these red entries are different. Okay. So yeah, one way to think about this is basically that sort of on each edge you have a variable, and basically this vector a1 up to ad that you assign with the v that kind of determines an assignment of these variables. And basically this f equal to 0 condition then says that this assignment has to be consistent in some way. Yeah, so the assignment that v puts on the edge vw must be the same that the assignment w puts on the edge vw. Okay, so this is the CFI construction. Well, the property that we get, I already indicated this at the first part of the talk. Two CFI graphs are isomorphic if and only if the sum of the f values or the sum of these function values over all edges, they are the same. So this basically means, f of VW equal to 1 corresponds to putting a twist on this edge. And then, the isomorphism type is determined whether the number of twists is even or odd. Okay. So here is again the picture that I've shown you before. So let me maybe briefly, first of all, connect these two pictures with one another. So the picture that you see here is not the graph that I've constructed on the previous slide, but they are very much related to each other. So basically the point here is that the graph that I've constructed on the previous slide, this only has for every gadget these inner vertices here. So for example, for the green vertex, these 4 vertices here in the middle, and I omit all of these outer vertices. So for example, this pair here and this pair. And well, for these middle vertices, for example, I put an edge between a green middle vertex and a blue middle vertex whenever there is a path here. So for example, between here and here, I put an edge because I have this path here that goes via the outer green and blue vertices from green to blue. Yeah, so in this way, the CFI graph that I've just constructed is kind of a more compact representation where I just leave out these kind of, outer things on the border of the bubbles and connect gadgets more directly. This is kind of more convenient to work with this more compact representation if you want to do things technically. On the other hand, if you want to show things and draw pictures, I think this thing that I have here in the picture is nicer because it allows you to illustrate this twist more nicely. Yeah, because if I omit these, or if I do the direct connections, then I have kind of a whole lot of mess between these 2 groups of 4 vertices, like we had here. You can't see a whole lot. Whereas here, with I introduce these intermediate vertices, you can see nicely the twist being present and not being present. Okay. But yeah, for the technical part, I will kind of assume that we work with this more compact representation, and that's also what we do with in the paper, because as I indicated, somehow technically it's more convenient. Okay, so now there was this other question by Jakob about having this global linear order. So here the thing is, basically what you can do is instead of writing this this tuple here in the second coordinate, which kind of gives values to the incident edges depending on the order, you can basically also put a function that says I map sort of incident edges to some values in F2 without specifying the order. That's completely fine for the Fürer-Leman graphs. It's a little bit annoying later with the identification, because we need to make sure to identify things in the right way in some way to not have kind of, yeah, so that things fit together. Okay, let me maybe explain this like this. So let's say you have, I don't know whether you can see when I'm drawing here, where do I have to move? Okay, so let me move. Yeah, so if I draw here, you can see. Okay, so let's say I have my two gadgets corresponding to VW. Is this visible? Or maybe I should stop sharing for the moment.
No, it's fine. It's fine. I think.
Okay, it's fine. Perfect.
Or at least for me, it's fine.
Okay. So I have I have VW on the top and I have V prime W prime on the bottom. And let's say later on, and here are some connections between them. Yeah, and later I want to identify the V gadget with the V prime gadget and the W with the W prime gadget. And then what I need to make sure is kind of that the edges that I have between them, they're identical. Yeah, so basically between these two gadgets, you put exactly half of the things. And well, if you kind of choose the opposite things and merge them, then you would have a complete bipartite graph between these two things, and you would lose all information. And that's something that you don't want. Yeah, you need to identify this so that you have kind of the same graph between these things. And well, putting this linear order on the vertices and numbering things is kind of one way to conveniently formulate this.
Is it correct if we zoom out a little bit and just think about this grid that you had before? Like when I start identifying vertices in the grid, then it's kind of nice to know for two vertices in the same row that their north edge is like the same and their east edge is like the same number, and their south edge is like the same.
Yes, but this is when also what you get by choosing any kind of natural numbering of the vertices. So I mean, you could kind of number vertices basically one row after the other or one column after the other, and basically then you get this property.
Yes. Okay. Yeah, but it makes sense.
But yeah, so since now I want to formulate things not only working for grids, but for arbitrary graphs, yeah, you will see later that this consistency condition comes up when we do the compression, and somehow putting a linear order is one convenient way to formulate it.
Makes sense.
Okay. So these are CFI graphs, and I have explained the connection to the graph that I have shown before. And yeah, here again, we can move around the twist. Okay. So with that, let's talk about twistings and yeah, things that allow us to move around the twist. Okay. So I say a G twisting, that's a set of edges. And here we have directed edges. And well, the point is basically, so the corresponding of a G twisting is that for every vertex W, yeah, the set of outgoing edges of W that are in the twist is always even. Okay, so that means, okay, and then I can define some notation. So a twisting twists an edge if basically one of the two directed versions is in my twisting, and it fixes a vertex W. Yeah, if none of the outgoing edges of W are in my twisting. Okay, so let me kind of explain the idea of a twisting on the previous picture. So let's look at the bottom part here. We want to move the twist, let's say from between green and blue to between green and between blue and orange. And basically this would correspond to the twisting where we have the two corresponding outgoing edges out of blue that in our twisting. Yeah, so I put the edge from blue to green in the twisting and from blue to orange in the twisting. Yeah, and then then what this means is that these two corresponding edges are twisted, and yeah, this is a valid twisting. And it kind of also corresponds to this, yeah, the mapping that I define out of this twisting. Yeah, and now if I kind of want to combine these things, so I want to kind of move from here between green and blue to
between orange and black, then I can basically just form the union of these two twistings. So I have kind of the two edges that go out of orange, and I have the two edges that go out of blue, which means now between blue and orange, both edges are present, and then this edge is not twisted. Yeah, and that corresponds basically, we do it twice, so nothing happens there. Okay. Yeah, so essentially these twistings allow us to describe automorphisms of CFI graphs. And yeah, in particular, isomorphism between two CFI graphs with certain functions fg that tell us where to place twists. They exist if and only if there is a corresponding g twisting, so that yeah, f is equal to g plus gt. So the function gt, that's what's defined here. Yeah, we put 1 whenever t twists our edge. And yeah, addition here is just, addition is just component-wise addition of the function, and everything, of course, over f2. Okay. So we have defined CFI graphs, and we have we have a way to define these twistings and move twists around and describe isomorphisms between CFI graphs via these twistings. Okay, so with that at hand, we can now move to the compression. So let's start by formally defining the compression. So compression is an equivalence relation on the vertices of a graph. Here we again have an ordered graph. And well, we have two conditions. So equivalent vertices are always supposed to have the same degree, and they are supposed to be non-adjacent. Okay, so non-adjacent is because then if we compress, then we sort of lose the edges between the corresponding gadgets, which we don't want. And of course, we need same degree because the size of a gadget, of a CFI gadget at a vertex depends on the degree of the vertex. And of course, if we do this compression, we cannot merge gadgets that have different sizes. Okay, so yeah, I think this makes a lot of sense to define a compression like this. And then we can also say that a function is compressible, well, if basically it respects this equivalence relation. So whenever I have v equivalent to v prime and w equivalent to w prime, then the function should have the same value. Yeah, and basically this exactly corresponds to the issue that I described before on the whiteboard. If I would have a function that is non-compressible and then I do the compression, that basically means I have kind of the opposing connections between the two edges, and I would lose the corresponding information. Yeah, I would merge these two things and get a complete bipartite graph, and this I don't want, and this is exactly formulated by this compressible condition that this will be avoided. Okay. So assuming that I have that, so I have a compression, and my function f that I put for the CFI graph is compressible. Well, in this situation, I can define I can define two objects. Well, first of all, I define this object that is drawn here, where I have these orange connections between vertices that I'm going to identify, but I'm not yet identifying them, but I describe this again with an equivalence relation. Yeah, so I have my CFI graph, and on top of this, I put the equivalence relation described by the orange edges. And then at the end, I have this CFI over the equivalence relation or expression, which is then really, I compress all the orange edges in this picture. Yeah, so these graphs here in the end, these are the small graphs that we are looking at. But this object here where we have the original CFI graph, but with the equivalence relation, this turns out to be very convenient for the analysis. Okay. Are there any questions regarding the construction?
Just curious. Do you need in this vertex identification, it seems like a natural constraint that if, let's say, UV is an edge and U prime V prime is an edge, and suppose you want to identify U and U prime and V prime.
Yeah.
Do you think you would require something like if V is the ith neighbor of U, then V prime should also be the ith neighbor of U prime, and
Yes,
symmetrically?
we will get to that. That will be a thing in a second.
So you do require, that's your answer, right?
Well, I mean, that depends. I mean, for defining this thing, I don't really require that, but I will. This will be relevant basically. So for the construction, it doesn't matter, but later when we describe the isomorphisms and the twistings, this will become relevant.
Okay, thank you.
So you're saying sort of that useful compressions will tend to have this property. It's not needed for the definition, but it's when you're analyzing the compressed graph, this might be helpful. Is that what you're saying?
No, I think for the yeah, probably this is
Okay.
somehow
maybe we'll get there. I mean,
yeah, I think you will need something like that basically to define useful twistings, because twistings will have this property, and twistings are the things that you need to move things around.
Sorry for insisting on this for one more second. I think it's like when I see these two, you said there's two induced objects, CFI comma equivalence relation and CFI quotient equivalence relation. I was having in mind that you were having games and you will prove some equivalence of rounds or something between these two things. I was thinking that probably there you would need something like this. So it's a semi-general level.
Yes.
Okay, thank you.
I mean, maybe we can, get back to this in a second, because, this condition will appear there. And then maybe it's better to discuss this after I defined everything. Okay, so if there is nothing else on the construction, then we can now get exactly to this point. So now we want to say, when we can work with twistings. And this is now exactly where this condition comes in. Yeah, so if I have a twisting, this is compressible. If, basically exactly this condition is satisfied. So if I look at two equivalent vertices, let's say this guy and this guy here, then I want basically if W is the ith neighbor of V and W prime is the ith neighbor of W prime, then the corresponding edges VW and V prime W prime, they're either both in the twisting or none of them is in the twisting. And this is basically, in the first part of the talk, this is this compatibility condition on paths, only that the twisting in general doesn't have to be a path, but it may be anything. Okay, so this is a twisting being compressible. And with this, we can now define kind of this abstraction of the k-compressible cops and robber game. So, yes, well, I hope you know the standard cop and robber game. So here we also have k-cops and we have a robber. The difference is the robber is located on an edge. The k-cops, as usual, are initially placed besides the graph, and then we place them on vertices or here on equivalence classes of vertices. Yeah, so each round consists of the following. Sorry for the typo. A cop is picked up, and well, the cop announces an equivalence class that he is going to move to. Yeah, usually this is described by the cop gets into a helicopter and starts moving to this vertex. And then the robber sees the helicopter approaching, and now he can move from one edge to the other. And well, here this is formulated by that we want to provide a compressible twisting that twists E1 and E2, and so basically the robber wants to move from one edge to the other edge, and he can do that if he provides a compressible twisting that twists exactly E1 and E2, and it fixes every vertex in a cop-occupied class. Yeah, so you can, so basically, the ping path cannot go through anything that is occupied by a cop, and it has to have this, this compressibility condition needs to be satisfied. Okay, and after that, the cop lands on the chosen class, and as usual, we want to catch the the robber and the robber is caught if both endpoints of the edge on which the robber is located are occupied by cops. Okay. So with that, we can now formulate the relations between the games. So we have winning strategies for robber and duplicator. And basically, so the thing here is, so if we have a winning strategy for robber on this K cops and robber game, on this G with the equivalence relation, then this implies a winning strategy for duplicator on these structures with the equivalence relation. And here we can also switch back and forth between this thing where we actually contract the equivalence classes. Okay, so there are some minor notes when going from kind of this bottom left to the bottom right. Duplicator survives only for 2 rounds less. Yeah, so if means if duplicator survives for R rounds on the left, then duplicator will survive for R minus 2 rounds on the right. So we lose kind of 2 rounds by the second step, but I mean, these are only 2 rounds, so that's not really that big of a deal. The second point here is that, between this compressed cops and robber and the bijective pebble game, this is not an equivalence that we have here. It is an equivalence if the equivalence relation is trivial. So if you play the standard CFI graphs and standard cops and robber game, this is the same. Here, okay, we haven't formally proved that it's not the same, but we expect that these two things are actually different. And essentially this has something to do with the fact that, these twistings that provide isomorphism, they need to satisfy this compressibility condition. And that means that, two compressed CFI graphs, they are not isomorphic exactly when, it doesn't depend on the parity of the twisted edges. But the conditions are somehow more complicated there. And the main sort of shortcoming is that in the cops and robber game, we don't allow the robber to be placed on multiple edges, which means having twists present on multiple edges, but we only allow it to be present on one edge. And this is kind of a restriction of winning strategies for duplicator in some way, which means that sort of when we describe these bijections, then they may only fail on kind of one edge in some way. And in general, when you don't have these equivalence relations, this is okay because you have always isomorphisms that fix things, but with these compressed things, you don't. So we may lose something here, and in a way this means that our lower bound is actually even stronger than our result is it says even more than this winning strategy here, because in fact we get a winning strategy in this case, which is more difficult to get. Okay.
Just a quick question.
Yeah.
So you're saying when you say that equivalence doesn't hold, you're saying that equivalence between the pair of parameters, namely the number of pebbles, or let's say the number of cops, and the rounds of the game that the robber can survive.
Yes, I mean, yeah. So
but it's still it is true that if I look at the number of cops only, then the number should be the same, or no?
Well, the point is just that this correspondence of games, that's just not there anymore. You cannot translate. So how is this if you have if you have a winning strategy for duplicator on these CFI graphs with equivalence relations, you cannot translate this to a winning strategy. So you cannot even translate this to a strategy of the robber, basically. Mm-hmm. That doesn't have a meaning. And kind of the point here is that if duplicator in this game plays a bijection, it may be necessary that you have errors on multiple edges, which would mean placing the robber on multiple. So there may be twists all over the place.
Yes,
And
I think you're saying that the robber can use not necessarily a path to move, but
yes,
like
exactly.
a tree
So if you
or
want to get an
forest.
equivalence, you would have to have some kind of weird condition that the robber can place some kind of weird twisting which twists any number of edges, and the robber is kind of located all over the place.
Okay, thanks for the clarification, but just one last minute. I think my question can be clarified as follows. So you showed that against a k-many or k+1, let's ignore that for a moment, many cops, the robber can survive very long. But the question I want to ask is that at least you know that k+1 cops can guarantee a win if you don't care about the wrong number. This has to be true, right? Otherwise, this is not a trade-off.
Yes. So I think you're basically saying that this one error, and then you're taking just a contra positive and use kind of, well, that games are determined. One of the players has to win. I feel, yeah, okay.
Yes.
Okay. Yes. So I think this is what I have to say on the first part. So maybe I'll give you a little bit more time to ask questions if there are any. And then I would move on to actually constructing a concrete G here and an equivalence relation so that robber can survive for a long time in this game here, and then basically it translates to the other two settings, where in particular this is the setting here that we want. Okay, so if there are no more questions, then let's continue. Okay, so now I want to describe the construction. So I need to describe the graph, and I need to describe the equivalence relation that we define. So we will fix some f of k, which we will set to 2k plus 2, and w sufficiently large. Basically, w somehow relates to the length of our grid. F of k is just some function in k that is large enough. If you're at some point you not feel happy that 2k plus 2 is sufficient, you may imagine some larger number. I don't know, 100,000 times k. This should always be sufficient. Okay, so then what we are going to do is we are going to pick some primes, p1 up to pk, that are all between w over 2 and w. So if you choose w sufficiently large, you can always do this by some prime density theorems. And, well, you construct a cylindrical grid. The rows will be indexed by 0 up to k minus 1, so k rows in total. And we have the columns where we have 1/2 times f of k times the product of these primes. And again, so that we can do modulo operations and stuff like that, I will start numbering them at column 0. Okay, and we construct the cylindrical grid, and the cylinder is basically on the rows. So the top row and the bottom row are connected. And yeah, for the columns, we really have this, columns with two ends. Okay, so that's the graph that we are considering. So now the equivalence relation. Well, I already indicated this in the first part of the talk. We have the periods, and the periods for the ith row is exactly this f of k times pi plus 1. Yeah, so two vertices are equivalent if they're in the same row, and the difference between the column indices is divisible by this period. And, well, then the only other thing that we make is kind of, we say there are no compressions at the beginning and at the end. Which means in the beginning, we just omit the first block of size, f of k times pi plus 1. So these are these kind of gray colored things here that we omit. And in the end, we also omit something. And what we want to make sure here is that we omit kind of a complete block. And the point is because we kind of had this factor of 1/2 there. The length of this grid may not be divisible by the period. So here we may cut off a little bit more. Yeah, so here kind of we may cut off like 1.5 of the last blocks because the last block doesn't quite fit in. So what this condition here just says is we want to kind of exclude one complete block and then whatever kind of remaining bit is there at the end. Okay. Yeah, note maybe that for the size of this thing, kind of these omissions here at the end, they don't really matter. Yeah, so in each row after the number of equivalence classes in each row is basically order f of k times pi plus 1. Yeah, we have kind of one such thing, f of k pi times pi plus 1 for these middle things. We have one here, we have one here, and then not quite one here, so it's less than 4 times f of k times pi plus 1 for the number of equivalence relations, so that's okay. This factor of 4 in the end disappears in the O notation.
Just to be clear, how long did you say were these parts on the end where you don't do any identification? Is it f
well,
of k?
Well, basically they should have at least this length here, so f of k times pi plus 1. But I want to kind of respect this block structure. Yeah, so if you have, let's say you look at the first row, you look at this period, f of k times p1 times p2, then you can kind of look first block, second block, you always kind of move these steps, and at the end it may not quite fit. You only get kind of one more kind of half a block in there. Yeah.
I see. Where will you need this like f of k times pi plus 1?
Well, this will be relevant in later proofs, but yeah, for the moment it's just a definition.
Okay. Thank you.
Yeah, so maybe the important properties I can mention here is that we have kind of this f of k is a part of the period in every row. So this is one important thing, and every prime number pi is a period in at least 2 rows. And in fact, in 2 successive rows. These are the 2 properties that we will need later on. Okay. And yeah, maybe I can just mention this. So how you choose these kind of these blocks that you leave out in the beginning and at the end, this is probably not so important. So the choice that we made here is kind of whatever was technically the most convenient. So we actually have done some experiments for k equal to 3, and there basically you could just leave these end things just of size 1 or 2, that was sufficient. So basically, yeah, these exact thresholds here in the last 2 bullet points, they're not so important. This is just the choice that we have made in the paper, and yeah, for the technical part, I will just stick with it. Okay, so this is the construction. And now we want to analyze this. And well, as you may remember from the first part of the talk, our basic strategy is always, well, we want to keep the robber at one of the 2 ends of the grid. Yeah, in particular, these 2 things where we don't do any identification. So here in the end, the equivalence classes are all singletons classes, and this is basically where the robber will kind of hide out for the game. And yeah, what we will need to, we need some possibility to move the robber from one end to the other in case the cops do not behave as they're supposed to behave. And if you remember the definition, that corresponds to the fact that we need to provide an end-to-end or a twisting, basically, that twists the corresponding edges. Yeah, so we need a twisting that twists one edge in the first part of the grid at the very beginning, and one edge at the end of the grid. And this now leads to this definition of an end-to-end twisting. Okay, so the imagination here is we have W. W is a set of vertices where the cops are currently placed. So here we really choose a set of vertices. Yeah, so you can imagine you pick one representative from each equivalence class where a cop is placed. And well, then we say an end-to-end twisting avoiding W. That's exactly a compressible twisting. So that's something that we need to move our rubber. And what we want to do is we twist edge in the first column, so here in the beginning, and one edge in the last column, so here at the end. Yeah, we twist no other edge. So we exactly have the two edges that we twist. We want to move the rubber from the one end to the other. And additionally, we fix all the vertices in W, yeah, and basically all equivalent vertices. So here, this is always the notation that I will use, kind of the union over all the equivalence classes from vertices of W. Okay, so this is what we need to move the rubber or the twist or whatever if cops are placed on W. Okay, so now let's try to find these end-to-end twistings that we need. And okay, so yeah, this is what I just said. The end-to-end twisting allows us to move the rubber from one end of the grid to the other. So these we now want to construct. Okay. And well, for this, we will consider some auxiliary equivalence relations, which are kind of coarser than the equivalence relations that we have in, or what's the, no, it's actually finer. So you kind of, you identify even more vertices in a way. Yeah, so what this means is if we can find end-to-end twistings, even with respect to these equivalence relations, that's kind of even stronger in some way. Okay. So the first thing that we do is we try to use two rows of our grids to send a twist from one end to the other. Okay, so what we do is we only look at two rows I and I plus 1. And well, to do this, we need to have this kind of, this compressibility or this compatibility condition for our path that we want to construct, that it needs to respect the periodicities. And the period or the prime number that appears in both rows I and I plus 1, this is this prime number pi plus 1, and of course this factor f of k. Yeah, so what we do is basically now we say vertices are equivalent whenever they have kind of this distance here. Yeah, their difference is divisible by this amount, which means it's kind of we make our equivalence classes larger, and we make it even more difficult to find such a compressible twisting. Okay, so we say a set is a pairwise separator for rows I and I plus 1 if we consider this set, close it under this relation, and it separates the first and last column in the grid induced by rows I and I plus 1. Yeah, so if we go back to the picture, so for example, here in the last two rows, so here in the last, so in both of these rows, we have kind of step size, what is it, 5 or so? Yeah, this is the step size that we choose. And here you can see if we have this step size, we don't have a pairwise separator on these two rows because we can still find this path from one end to the other. Okay. And sort of the key observation here is, if we do not have such a pairwise separator for rows I and I plus 1, then we can kind of build this periodic path that was already indicated on the last slide to build an end-to-end twisting. Yeah, we just repeat every f of k times pi plus 1 columns. We repeat the pattern of this path. And then it respects this equivalence relation, and in particular, it respects the equivalence relation that we are interested in because there less vertices are equivalent. Yeah, in that case, we have even larger periods that are multiples of this. So things are also okay. Okay. So
but we're sort of restricting ourselves here. I mean, in some sense, I mean, a priori, the rubber could sort of move all over the place, but in order to not get a headache, we're sort of really
yes.
just going to use these two rows.
Yes. So we are kind of trying to find nice ways of how we can move the rubber from one end to the other. And in the end, it turns out that these nice things are somehow sufficient. Yeah, and here we are kind of, restricting us to rows I and I plus 1 for every possible I. Okay, and then that's what we call a pairwise separator. Okay, so if there is not a pairwise separator, then we can move from one end to the other. So now there is just one more situation where we can move from one end to the other. And that's basically the situation where, let's say, we repeat our things every f of k columns. Yeah, so we take W and we use the equivalence relation where we repeat every f of k steps. And this is basically because this period f of k, or this factor f of k in the period appears in every row. So here basically the rows kind of don't matter, and we consider all rows at the same time. And we say that, if also we have this kind of separator here, so this also separates the first and last column, then we have a pseudo separator. Yeah, and well, we can generalize the last result. So if we have not a pseudo separator, then we also have an end-to-end twisting. Yeah, not the pseudo separator means that either we are not a pairwise separator, then we have already seen it, and otherwise basically not even this thing is a separator. Yeah, and then we can kind of use all the rows at the same time, but we kind of repeat every f of k steps, this periodic path. And this is also okay because f of k is a factor in the period in every row. And yeah, intuitively, this is needed to kind of accommodate for the fact that separators may not be on one column, but they may also be kind of diagonally and span, let's say, up to k consecutive columns. And to handle this fact, you need to kind of allow this second option in some way. And this is basically why this f of k comes into play. Yeah, we also, I mentioned this briefly in the first part. Okay, this is maybe not, well, it's actually kind of a good picture because, yeah, this guy here, for example, no, it's not. Well, no, here we don't have, okay, but you may remember it from the first part of the talk. That when we put this additional rows between there to, kind of accommodate for this problem. And somehow this is reflected in this second condition here. Okay. So that's a pseudo separator. And yeah, here's the corresponding picture where I put things in between. Okay, so basically the situation is if the cops play on a pseudo separator, then we cannot move the robber from one end to the other. And at this point, the main insight is that if we have such a k-vertex pseudo-separator, so we have k vertices in our set W, then there is at most one SW in the corresponding equivalence class closure thing that separates the first and the last column. Yeah, so here you can see the picture. We have kind of, we block four rows here with one equivalence class in each row. And this here is our unique separator that we identify. Everything else that we have is not a separator. And well, on top of that, even if we have a second k-vertex pseudo-separators that differ, and both of these basically differ only by one element, then the corresponding unique things, if they exist, that we get, they also differ by at most one element. And actually, these two elements are very close to one another. Yeah, and what all of this basically allows us to do is always say, well, as long as the cops play pseudo-separators, then there is this unique separator, and you can kind of, in each step, only move it forward by a bit. Basically, you can, in one round, you can basically move, one log, one forward to the next column. And you always have to kind of preserve this moving forward. Yeah, and these two things basically allow us location of the pseudo location of the separators that we want to track. Yeah, the first thing says there is always one exact location that we can fix, and the second one says if the cops make one move and we still have a pseudo separator, then the location of the separator that we identify, it can only move forward by a bit. It doesn't move a lot. And yeah, if you then have these 2 points, that means that you can essentially implement the winning strategy just as on the standard grid, without these equivalence relations. Yeah, the robber is always hiding on one of the two ends. If we don't play a pseudo separator, then we can use this end-to-end twisting to move from one end to the other. And if a pseudo separator is placed, then kind of we look at this location. Well, when it's first placed, we move to the end that is further away. And after that, it kind of the separator has to be moved step by step to the corresponding end until the robber eventually can be caught, but only after omega of length many iterations. Yeah, and this is basically formulated here. So we require omega of length grid many iterations, which is omega to the k, but the compressed graphs have only order of w square many vertices. Yeah, remember w was roughly the size of all the primes that we had. Okay. Yeah, I think I have used roughly the 1 hour that was allotted for this slot. So let me just show the conclusion slide here again. And thank you for your attention. And if there are any questions left, then feel free to ask.
Thank you so much, Daniel, also for this second half, which is again very helpful, and in particular the illustrations are really helping to make this highly intricate paper a bit more accessible.
Thanks.
I guess we asked a fair number of questions already during the presentation, but let's open up the floor if there are any final questions or comments. I guess one obvious one is, having this slide. So what, what's your bet? What are the right answers here? You have any feeling for, like, is it n log n or n in the k equals 2 case, and is n over k half or n over k plus 1?
I mean, if in the general case, I would tend to n to the k minus 1, but that's I mean, in this other paper, so in this paper here, we have kind of a technical lower bound, which is kind of very curious. So we defined some weird extension of WL. And in this case, the right answer is actually n to the k minus 1. So we have a lower bound of n to the k minus 1 for this weird variant, which basically in the Lix paper, we used to argue that kind of with the techniques currently for upper bounds that we have at hand, we cannot go any further because they also tend to work in this weird setting. But yeah, to some extent, it makes me also believe that n to the k minus 1 is the right answer for the real Weisfeiler-Leman. But yeah, on the other hand, one should also mention that if you look at these trade-offs and the robust setting, there we have an upper bound of n to the k over 2. So that's also kind of an interesting fact that we have this non-robust lower bound of n to the k over 2 and robust upper bound of n to the k over 2. Also some kind of weird coincidence.
So I guess for Weisfeiler-Leman, and also for this, as far as I understand, these fragments of first order logic with counting quantifiers, this question of how the number of variables and the quantifier depth, the trade-off between the two, is something that people have identified as a question and care about, and it carries over sort of naturally to proof complexity because there are intuitive correspondences to these measures. But do you know also, like, I don't know, over, say, in machine learning or something, would there be, like, what kind of properties of Weisfeiler-Leman do they care about? And would they also, like, would these results have some kind of interesting applications or information in such contexts?
Well, depends. I mean, okay, so one thing that they care about is this kind of properties that can be identified by very low dimensional Weisfeiler-Leman, because I mean, this is what they can manage. I mean, in machine learning, you can't manage to run 10-dimensional Weisfeiler-Leman, but maybe if you're lucky, you can do something with 3WL. And also something that they like to do is sometimes they only run the algorithm for a few rounds. with the idea to avoid overfitting. So then maybe one thing that's interesting for them is things that you can identify quickly, let's say, but that's kind of yeah, it's fairly vague, I think.
Fair enough. Okay. Any other questions or comments? Otherwise, I think I just want to say a big thank you again for this tour de force. It was an amazing seminar. Thank you so much. And yeah,
happy to
we're
be
really
here.
okay. Thanks again. Thank you.
Thank you.